Hi, my name is Kiran Baburaj. Welcome to Career Campus Pro YouTube channel.
What if I told you the same algorithm that decides which patient get treated first in an emergency room is also determining which social media post you see first? It's called the Heap. It's silently working behind the scenes of your daily life. In the next few minutes, I'll show you how this powerful data structure works, why it's so efficient, and how understanding it gives you the glimpse into the invisible algorithm that shape our modern world. Heap is just a complete binary tree. It means all the levels of the tree are filled completely, except possibly the last level, which is filled from left to right, where every node follows a specific ordering property with respect to its children. So let's look at some of the key properties that make heap so useful. First, we have the constant time access to the root element, which is either the maximum or minimum value depending on the heap type. Second, there is a clear parent-child relationship in a heap. For any node at index, its left child is at index 2i plus 1 and right child is at index 2i plus 2. This mathematical relationship makes heaps easy to implement using arrays. Third, the complete binary tree structure ensures that our heap always maintains a balanced shape, with nodes filling each level from left to right. Fourth, this structure allows heap to efficiently implemented using simple arrays, despite of being conceptually tree-based. And finally, the height of the heap is always logarithmic, that is order of log n, where n is the number of elements. This property is crucial for efficiency of heap operations. Further, we have two main types of heaps. In a max heap, the parent nodes are always greater than or equal to their children. This means maximum element is always at the root. And in a min heap, the parent nodes are always less than or equal to their children, placing the minimum element at the root. These properties makes heaps perfect for quickly finding maximum or minimum values. Next is heap operations. The first is insertion. We add a new element at the bottom right position and then bubble it up to its correct position. Next is extraction. To remove the root, we place it with the last element and then bubble it down to maintain the heap property. And next is peak. It gives us access to maximum or minimum element depending on the type of heap with order of 1 time complexity. Heapify. It's a process to rearrange the elements to maintain the property of a heap data structure. That is done when a root is removed. We replace the root with the last node and then call the heapify to ensure the heap property is maintained. Or heap is built, we call the heapify from the last internal node to root to make sure that heap property is maintained. And this operation takes the time of log n. As we have discussed earlier, heaps have numerous practical applications such as powering the priority queues in an operating systems. They are essential for efficient heap sort algorithms. They optimize the graph algorithms. They are also used in job scheduling systems. The efficiency of heaps is impressive. The insertion takes log n time. Extraction of minimum or maximum elements takes log n time. Peaking the maximum or minimum element is constant time, order of 1. And building a heap from the arrays takes just order of n time. Heaps are truly powering the modern technology, from the apps in your phone to critical infrastructure systems. Understanding this fundamental data structure gives us insight into how our digital world efficiently organizes and processes information.
If you found this video helpful, please don't forget to like and subscribe. Happy coding. Thank you.